Okay, so we're into chapter 5 now, and Bruce, chapter 5. It's lesson 16, and we're really getting into organic chemistry now. So this is, I admit, I'm tempted as a professor to be excited about this. This is some cool stuff. So what we're going to do in chapter 5 is we're first of all going to talk about alkenes. Alright, their structures and their properties. But then, and this is the exciting part, we're going to begin to talk about reactions, which is what organic chemistry is really all about. So, I'm going to divide this lesson up into 2 videos. The first one, and I'm not even sure how long they'll be, but that's not really the point. The point is that there's 2 major points that we're doing here. First of all, with lesson objectives 1 through 3, we're talking about alkenes and their structure. And then what do structures mean? What does structure mean? Why is it interesting to us? Well, because of these last 2. Okay. So first of all, the structure, and then the reactions that we're going to get from those. So let's start with the first thing, and that is calculating the degree of unsaturation. Now this sounds like a bit esoteric in the beginning, but let me try to establish why this is valuable. If you have a formula that's, say, C4H10. You did this in one of your first lessons this term. C4H10 suggest possible structures for this, and we're also doing this with spectroscopy right now too. So this will be on the midterm. This concept will be on the midterm, even though it's in lesson 16. C4H10. What could C4H10 be? Well, it could be 1, 2, 3, 4, right? And if we count the hydrogens here, we'll see that there are 10 hydrogens. It could be 1, 2, 3, 4, right? And that's it. That's all C4H10 can be. Okay? What could C4H8 be? Alright? Bear with me here. Stick with me. This is going to be important. C4H8 could be 1, 2, 3, 4, that. 1, 2, 3, 4, that. 1, 2, 3, 4, that. Or 1, 2, 3, 4. Okay? These are all C4H10. I'm sorry, these are all C4H8. Alright? What could C4H6 be? It could be 1, 2, 3, 4, that. 1, 2, 3, 4, that. Which that would be linear. That would be sp hybridized for reasons which are perhaps obvious to some and not so obvious to others. Okay, but either way, that's a possibility. Or 1, 2, 3, 4. Yeah, there's 1, 2, 3. Okay, that's a possibility. No, that's not a possibility. That carbon's got 5 bonds. Sorry. 1, 2, 3, 4. I guess these are the only possibilities here for C4H6. All right. So my point is, the term that we're going to use here is degrees of unsaturation. Right. So we get to this point here in the text. And we start out with some formula that looks something like this. For a saturated alkane, it's going to be, the formula is going to be CnH2n plus 2, right? And I know some of you right now are your heads are hitting the table. This is too boring to possibly be valuable. But I'm going to tell you that we are going to use this to simplify things for ourselves in the future, and so perhaps that can keep you awake. CnH2n plus 2. So what do we mean by that? So I start out with C4H10, and since it was C4H10, you see how this is n is 4 here, and so 2n plus 2 is going to be 10. So I immediately know that there are no double bonds and no rings. Alright? Immediately know that. Another way to look at this is that there are as many hydrogens as possible in here. As many as possible. Okay? So looking at the simplest one, if we have a carbon, just one, CH blank, okay? You can see how many are possible here, right? There are 4 hydrogens possible just by looking at that. Okay? And what about C2H blank? Can you see that 6 are possible? Right? What about C3 blank, right? Can you see? Okay, so you can perhaps see the pattern what I'm doing here. Now I'm going to be taking these terminal carbons and just drawing them down, and I'll be adding CH2 each time, right? All right, well, you get the same thing if you get, look at this, here's 4, okay? It's going to be a little costly to draw all the hydrogens in there, which you'll have to do, right? But for the purpose of this video, I'm not going to do that to save time. But look at this, okay? I still have the same possibility for the number of hydrogens on here if I have a branched. So branching is not an issue, but if you have a formula of CnH2n plus 2, you have no double bonds and no rings. Because if I have this, I now have fewer possibilities for hydrogens. Okay, so again, the term is saturated, and there's several ways to get here. You might want to start with the formula and just prove it to yourself, or you might want to start with the formula and the conclusion of that and prove it to yourself. All right, so and prove it to yourself that way. It doesn't really matter how you get there. I guess the point is, for every degree of unsaturation, what we're going to be doing, let's look at a simple molecule here. For every degree of unsaturation, we're going to be taking away 2 hydrogens. Okay? So if I make, let's say a degree of unsaturation would be a double bond or a ring. If we take away 2 hydrogens and put a ring there, I'm sorry, and put a double bond there, then we have 1 degree of unsaturation. Okay? You can see I still have 4 bonds to my carbons. All right, so this is going to be a little abstract, but you really need to work with it a little bit. You may want to come back to the formula. I'll tell you, I worked on this for years and years without ever using the formula. Only recently have I started to present that, because I found that some students do prefer that. And it's going to help some students, but not everybody. And I'll admit, in class, I might refer to it when I'm solving problems, or I might just do it a little more intuitively. All right, so that's degrees of unsaturation. And the next thing that we're going to do, and the only other thing we're going to do for this video, is we're going to talk about the Kahn-Ingold Prelog rules. And what does that mean? All right, so we want to show ourselves, first of all, that how we're going to name this, okay? All right, so if this was a straight chain alkane, we would name this ethane. Right? But in this case, remember the rules for nomenclature? Number 1, identify the principal functional group. In straight chain alkanes, it was none. In alcohols, it was hydroxy, right? Or all would be the ending. And number 2, identify the longest continuous carbon chain. Identify all substituents and then alphabetize. Put everything together. All right, so in this one, we would say it's ethane, but then we would change the ending to accommodate the principal functional group. Ethene. All right, we identify all substituents. There are none. And then we alphabetize. There are none. So this is the name of it. It's ethene. But what if we have something like this? Okay? So number 1, identify the principal functional group. It's an alkene. Number 2, identify the longest continuous carbon chain. 1, 2, 3, 4. Right? And then the next thing we do for rule number 2, we identify the longest continuous carbon chain. We change the name to accommodate that. Number 3, identify all substituents. There are none. Number 4, alphabetize. There are no need for alphabetization because we don't have any substituents. All right, so that's the name, butene. All right, but here's the problem with this. The problem is that and this are not the same structure. Why? Because there is no free rotation. About that double bond. Remember that structurally stuck? Okay, no free rotation. There's a pi system here. There's a pi orbital above the plane, a pi orbital below the plane, and it cannot rotate. All right, so these are 2 different molecules. Well, how do we deal with that? Well, first of all, you have to identify if it exhibits this isomerism or not. These are isomers, one of another. These are structural isomers. Okay? These are structural isomers, and you've got to be able to identify if it exhibits isomerism or not. Okay? Does this exhibit cis, trans, or EZ isomerism? Okay, that sounds like an easier question than it really is. Let me give you an example of one that looks like it. You might think, well, gosh, everything that's got a double bond must exhibit cis-trans isomerism. But that's not so. What about that? Does that exhibit cis-trans isomerism? Is it the same as that? Yes. Therefore, it does not exhibit cis-trans isomerism. It does not. Okay? So how are you going to figure that out? You can't just look for double bonds. The way that I'm going to do that is I'm going to take the double bond compound that I've got, okay, and I'm going to redraw it. And I'm going to leave one side of the double bond the same, and I'm going to take the other one and switch it around. Well, if these are methyl groups, which I've implied that they are, right, they're just sticks, then the other methyl goes there and the other one goes there. Is it the same molecule or not? Still, same. Therefore, does not exhibit cis-trans isomerism. Okay? But let's look at another one. Boom, boom, boom. Okay? So what I'm going to do, again, is I'm going to redraw this thing. I'm seriously going to do that in my mind, because we're going to get some complicated things on the exam, right? So you need to have a simple method. So I'm just going to take that double bond, cut it in half, leave one side the same, and redraw the other one. Is it the same thing? No, it's not. Not the same. Okay, can you see that? All right. So the next thing we need to do is we need to say how do we deal with cis-trans isomerism? And the way that we deal with that is we say that in cis-trans isomerism, if these two groups, circle and circle, right, which are two methyl groups, if they're on the same side, they're called cis. If they're on the opposite sides, they're called trans. Trans may be a word that's easier for you to sort of fit in your intuition. Cis is not a word that we use in regular common, everyday English a lot. We use that for cyclohexanes, but here's cis and trans, okay? So this is trans 2-butene. What is this? What is that? Okay. Now, cis-trans isomerism is only good if you've got a hydrogen on both sides. Okay? But what if you don't? This is a tricky one now. If it's tricky, tricky. Okay. If we don't have a hydrogen on both sides, we can't use cis-trans isomerism. We're going to use EZ. Okay, which is basically the same thing. Cis and Z are basically the same thing. All right, and trans and E. It's just a little more elaborate. So what we do here now is we look at each side individually. Okay, let's look at this side first and say, where's the bigger group over here? There's a hydrogen. I'm going to circle the bigger group over on this side. Then I'm going to come over to this side and circle the bigger group over here. Are the bigger groups now on the same side? Yes, they are. If they're on the same side, Z, same, Zide. All right, it's a bit goofy, but my professor said, and I think I've seen pictures of this sort of cartoon of a German who used lots of Z's, right, with a lot of hair, big huge mustache, scientist saying, that these two big groups are on Z, same, Zide. All right. And that's the way that I remember it. And then, of course, if they're not on the same side, then... Right, there's the bigger group on this side. There's the bigger group on that side, right? There's the bigger group on that side. And they're opposite sides now, so that would be E. Okay, so let's name this guy. 1, 2, 3, 4, 5. All right, first of all, step 1. Identify the principal function group. It's now key. All right, now we got to find the longest continuous carbon chain with the principal function group in it. 1, 2, 3, 4, 5. Now we've got to change that ending to accommodate the principal function group, pentene. Okay, now we've got to identify all substituents. Here's the only substituent that I didn't name. That's a methyl. How do you spell methyl? Methyl. And we've got to say where it is. All right, so 1, 2, 3, 4, 5. I think that's going to give us, see, the double bond is closer to that end, so we're going to say that this is 1 over here. So that's going to be 3 methyl pentene. But you know what? We never said where the double bond was. All right, so the double bond is at the 2 position, so it's 2 pentene. 3 methyl, 2 pentene. All right, really, the double bond is at the 2, 3 position, right? It's between carbons 2 and 3. But since you know that the other carbon is going to be immediately following it, you only name the first carbon. So it's 3 methyl, 2 butene. All right, let me conclude this video with the one trick, I think, which I sort of implied with that last picture. The one trick, the thing that stumps people sometimes is, watch this. 1, 2, 3, 4. Okay? So you've got a methyl group here, CH3, CH3. This would be tricky. This is the same molecule we had before, okay? But this would be tricky, because you see the methyl groups are on the same side, but that's not what we're asking with EZ. With EZ, we're not asking, are the methyl groups on the same side? Actually, let me leave that as a question. What are we asking? All right, be thinking about that. That would be a good quiz question. Why is, do you see how these guys are on the same side? But why is this E? Wow, good question. All right, we'll end the video with that and talk about it more in class.